So in this video, let's talk about the ideal gas law. So what does this ideal gas law tell us? Well, it essentially tells us if you have a container with gas, and if you know the pressure of the gas and multiplied by the volume of the container, that will equal the number of moles in that gas multiplied by the ideal gas constant multiplied by the temperature in that container. But really, what does this mean? What is this equation trying to tell us? Well, what is a pressure? A pressure is just a force per surface area. And what is a volume? A volume is just a length by length by length, meters cubed. So what happens if you multiply pressure by volume? Well, we know these units will cancel, and we'd essentially be left with Newton meters, which is joules, which is energy. Which is pretty interesting. If you know the pressure of a container and you know the volume of that container, you can determine how much energy is in that container. You can determine how many joules of energy is in that container. But what does this side of the equation tell us? Well, what are the units of the ideal gas constant? It's just joules per mole Kelvin. And again, what is this N? This N is moles. What is this temperature? This temperature is Kelvin. So if you multiply all these units, the moles will cancel and the Kelvin will cancel. And again, you're left with energy. You're left with joules. So this is another way to determine how much energy is in this system. If you know the number of moles of gas and you know the temperature of the container and you multiply by the ideal gas constant, that would give you joules. That will tell you how much energy is in the system. So these are two separate ways to find out how many joules are in this system. So let's try an example. Let's say we have this system, and let's say the system has a pressure of 3 pascals. Let's say it has a volume of 3 meters cubed. Let's say we know there's 1 moles of gas, and let's say it has a temperature of 3.61 Kelvin. How do we use these variables and plug it in to solve for this ideal gas law? Well, first of all, we know if you know the pressure of a system and multiplied by the volume of that system, that will tell you how much energy is in that system. So we know this system has a pressure of 3 pascals and has a volume of 10 meters cubed. So therefore, we know this system has 30 joules of energy. And that's what this side of the equation tells us. It's one way to find out the energy in a system. But we also know if we know the number of moles in a system multiplied by the temperature in the system and multiplied by the ideal gas constant, which again is just a constant you can find in any textbook, then that's a way you can determine how much joules of energy is in that system. That's another way to determine the amount of energy in a system. So whenever you know the number of moles in a system multiplied by the temperature of that system and multiplied by the ideal gas constant, you can determine how much energy, how many joules of energy is in that system. However, the way I like to use this equation is I like to divide both sides by temperature. So you divide both sides by temperature. And if you do that, you're left with this equation. The pressure of the system multiplied by the volume of the system divided by the temperature of the system equals the number of moles in the system times the ideal gas constant. However, something important to realize is if we keep the number of moles constant, which is a reasonable assumption, assuming we don't make new molecules or lose new molecules, so if we keep the number of moles and the number of molecules constant, then we need to realize the ideal gas constant, this is just a constant. R is just a constant. So if the number of moles is also constant, then this entire side will be a constant. So that's a very important implication because if this side is constant, then it doesn't matter how we change the pressure, volume, or temperature. We know this value will always just equal a constant. So let me do an example to help illustrate this. So let's say, again, we had this initial system. We had a system with the pressure of 3 pascals, a volume of 10 meters cubed, and a temperature of 3.61 Kelvin. And let's say we had 1 mole of molecules, and let's say that's constant. So if we were to plug in all these values, we'd be left with this. So again, we plug in the pressure, volume, temperature, number of moles, etc., and we would be left with this. But again, if the number of moles is constant, we know the ideal gas constant, this is just a constant, it's always 8.314 using these units. Then if the number of moles is constant, then we know this side will just be a constant. So this will just equal a constant. So it doesn't matter how we change pressure or how we change temperature, etc. We know how the other variables have to change because we know this side will still have to equal this constant number. So the key point, whenever you have a system where the number of moles is not changing, then if you take the pressure multiplied by the volume and divided by the temperature, it's going to equal a constant. So it doesn't matter how you change any of these variables, you know this entire side has to remain constant. However, if you increase the temperature, how are these other variables going to change? Is the pressure going to increase or is the volume going to increase? Or are they both going to increase a little bit to keep this ratio constant? Well, a couple rules of thumb are these. These are a couple rules of thumb. So I recommend just taking a screenshot and memorizing this, but we can do some examples. So let's say we kept the volume constant. So let's say the system was rigid. It was in a rigid container where the volume is constant. And let's say we had a pipe and we pumped in air and we increased the pressure. What's going to happen? Well, if we increase the pressure, we know the temperature must increase because that's the only way to make this ratio constant. Because if we increase the pressure and kept the temperature the same, then this constant would increase. And that doesn't make sense because remember, this side is a constant. So therefore, if you increase the pressure, the only way to allow this ratio to remain constant is by increasing the temperature. So let's try another example. Let's say we kept the temperature constant. So let's say the temperature is constant. What happens if you decrease the volume? If you squish this and decrease the volume? Well, if you decrease the volume, you know you would have to increase the pressure because that's the only way to allow this to remain constant. So that's another rule of thumb. The last rule of thumb is let's say we kept the pressure constant. Then what happens if we increase the volume? So let's say we expanded this container and we increased the volume. Well, if you increase the volume, you would have to increase the temperature because that's the only way to allow this ratio to remain constant, and we know it has to remain constant. So those are just a couple rules of thumb. So the key point, as long as the number of moles is constant, then if we take this pressure multiplied by the volume and divided by temperature, we know it's going to equal a constant. As long as the number of moles is constant, we know this is just going to equal a constant. And to make this a little more concrete, let's put in a number. Let's say we took the pressure multiplied by the volume and divided by the temperature, and that equaled 10. Then it doesn't matter how we change these initial conditions. We could change the pressure, or change the volume, or change the temperature. It doesn't matter. Once we have these new final conditions, if we take this final pressure multiplied by the final volume and divided by the final temperature, it would still equal 10. It would still equal that same 10, that same constant. Because again, this equals a constant that's not changing. So it doesn't matter how you change any of these variables, it's still going to equal 10. So another way of looking at this is if you have this initial system and you take the pressure, volume, and divided by temperature. It doesn't matter how you change the system and now you have these new final conditions. If you take this pressure, this volume, and this temperature, it's going to equal those initial conditions equaled. So that's another way of looking at this system. The initial pressure times initial volume divided by initial temperature will always equal the final pressure times final volume divided by final temperature, as long as the number of moles is constant. So let's try one last example. Let's say we had this system, and let's say the pressure was 3 pascals, let's say the volume was 10 meters cubed, and let's say the temperature was 3.61 Kelvin. And let's say the number of moles is constant, so we know this side has to equal a constant. So let's say that constant happens to be 8.314 joules per coulomb. Then we know it doesn't matter how we change any of these variables, we know it would have to equal 8.314 joules per coulomb. For example, let's say we doubled the temperature and kept the volume constant. So let's say the volume was kept constant, but let's say we doubled the temperature. Well, if we double the temperature, we know we would have to double the pressure because that's the only way to allow this to still equal 8.314. And that's just simple math. If we double the denominator, we would have to double the numerator to allow this ratio to still equal 8.314. But another example, so let's say we decrease the volume by half. So let's say we halve the volume while keeping the temperature constant. So if the temperature is constant, but we halve the volume, so the volume is cut in half. If the volume is cut in half, we would have to double the pressure because that's the only way to allow this to still equal 8.314. So the point is, if we have a system and the number of moles is constant, if you take the pressure multiplied by volume and divided by temperature, if it equals a number, then it doesn't matter how you change the pressure, how you change the volume, how you change the temperature, this value will still equal 8.314. And then you can change a variable again. It doesn't matter if you plug in all these values, it will still equal 8.314. So the point is, if you have these initial conditions, plug in the pressure, volume, and divided by temperature, it doesn't matter how you change the conditions. Once you have the final conditions, if you plug in the pressure, volume, and divided by temperature, it will equal that same value. These two values will equal the same. So this is the ideal gas law. And the key point is if you know the pressure of a system and multiplied by the volume of a system, that tells you the energy in the system. Also, if you know the number of moles in a system multiplied by the ideal gas constant and multiplied by the temperature of a system, that will also tell you the number of joules in the system. However, one last implication of this ideal gas law is, let's say you know the molar mass of the gas molecules in the system. Then you can multiply both sides by that molar mass. So we know the units of molar mass is grams per mole. So let's say we multiplied the molar mass to both sides of the equation. And we can do that. As long as we multiply both sides by the molar mass, that's okay, because we're doing it to both sides. And realize this N just represents the number of moles in the system. So therefore, these moles can cancel. So if these moles cancel, we're left with grams on this side. So we're left with grams, so we're left with this equation. And rather than writing grams per mole, let's just represent this with an M for molar mass. So again, this represents the molar mass of the gas in the system. So now we can divide both sides by volume. We can divide both sides by volume. And if we divide both sides by volume, these volumes will clearly cancel out. And we'll be left with grams divided by volume, which is density. This equals density. So if we divide both sides by volume, if you follow the math, you would see we'd be essentially left with this. We'd be left with the pressure of a system multiplied by the molar mass of the gas in the system equals the density. Remember, we got density by grams divided by volume. The density of the gas times the ideal gas constant multiplied by the temperature of a system. So we're left with this new equation. And now dividing both sides by RT, if we divide both sides by RT, we'd be left with this equation. So just doing some simple rearrangements, we're left with this equation, which essentially tells us if we know the pressure of a system multiplied by the molar mass of the gas in the system and divided by the ideal gas constant and the temperature of the system, it'll equal the density of the system, the density of the gas. So this is another form of the ideal gas law. So if you're doing the MCAT or a chemistry question and you're given the molar mass or you're given the density, there's a good chance you need to use this equation. Or maybe you need to solve for the density, or maybe you need to solve for the molar mass. It's a good sign you need to use this equation. So again, this is the ideal gas law. This is the way I like to use the ideal gas law. And this is another implication of the ideal gas law in reference to the density and molar mass of the gas in the system.